morning. I hope you're able to see my slides.
Yes, sir.
So in the last class or last few classes, we worked out steady state solutions of the cable equation. Right? We began with we were last class we worked out the finite cable, right, under two boundary conditions, the sealed end and keeled end boundary conditions. In case of sealed end, you have RL is equal to infinity, so it's an open circuit. In case of keeled end, RL is equal to 0, that's a close, short circuit, right? So then we have the more general case where RL is finite. So let us work this out. And we also said that the interpretation for the arbitrary and loading case, that is that, let me share the, yeah. So the interpretation here is that, I think I mentioned in the last class, you'll generally have a dendritic tree, right, where you have so a main branch and then lots of smaller branches and so on and so forth, right? So if you are considering the voltage in this main branch, right, then you should reduce the entire, should be able to reduce the entire, all the other branches into one resistance and call it RL. So if you can do that, and then you'll have a setup like this, where there's a cable, and then at the end of it you have some kind of loading resistance. So now how do you, this is a more general case compared to other two that we've done. So how do you now work out the voltage, steady state voltage distribution in a cable like this? So loading resistance is RL, and we assume that the input resistance or the resistance of the X equal to 0, right, is V naught. Now how do we solve this? So let us assume a new quantity here, this point, I'll call this VL. That's a loading voltage. This is at X equal to L. Right. Now the voltage expression is just like before, A cos H L minus X plus B sin H L minus X. I've given the justification for this in the last class. So if this quantity is equal to VL at X equal to L, I just plug in X equal to L, then you get cos H of 0 plus A cos H of 0 and B sin H of 0. So this part vanishes. So you'll get A equal to VL. Right, so you have that, then plug this back into this equation. And one more thing that you can do here is at X equal to 0, the voltage is V0. So we have assumed some quantities. We're given names to the voltage at the input point and the the output point. So that is X equal to 0 by X equal to L. So V0 and VL. So if you assume that X equal to 0, Vx is V0, then X equal to 0, you have A cos H L plus B sin H L. Okay, so and A is VL. So you get B equal to V0 minus VL cos H L by sin H L. So we have now expressed A and B in terms of VL and V0. So you plug it into this expression again, these new values of A and B, plug it into this equation. Then you have the slightly more complicated expression. So note that for the arbitrary ending, the algebra is a bit more complicated than the previous two. But just bear with me and we'll go through the derivation slowly. So Vx is equal to VL, the cos HL minus X. So if you plug in V equal to this whole thing here, you get V0 minus VL cos HL by sin HL into sin HL minus X. So now take the sin HL in the denominator and move things around. You get in the numerator VL cos HL minus X times sin HL plus V0 minus VL cos HL into sin HL minus X. So now you see that the numerator has three expressions or three terms. This one, then second term is V0 sin HL minus X. Third term is minus VL cos HL sin HL minus X. So now we know from the hyperbolic function summation rules that sin h of A plus B is equal to sin HA cos HB plus cos HA sin HB. Okay, and again sin h of minus A is equal to minus of sin HA, because sin h is a is an odd function, cos h is an even function, just like the sine and cos. So if you use that, you have this expression. If you invoke this expression given here, sin h L cos h L minus x minus cos h L sin h L minus x is equal to sin hx. It reduces to a very small expression. So this is what applies here. So if you plug this in, you get VL sin h L minus VL sin hx plus V naught sin h L minus x by sin h L. So this is what you will get. This is just a simplification. We still have the basic problem of finding out VL, because VL we have just assumed some name to it. We need to solve it and find out what it is. Okay, so how do you find out VL? We need to find out. So what did we do in the last two cases? We find out the axial current at the far end of the cable, right? Then, so if it is an open circuit, then the axial current is 0 and things like that. So similarly here, to find out VL, we need to find the axial current at the far end, right? So axial current is given by I is equal to minus 1 by Ra times dou V by dou x, dou small x, remember that. So if you use this expression and differentiate this with small x, so note that the expression in all these expressions, the expression is expressed in terms of capital X, which is small x by lambda, but the derivative is with respect to small x, right? And that can be a cause for confusion, but you need to be careful about that. So if you differentiate like that, you get 1 by x out, right? Because the derivative with respect to small x. And you have this remaining expression. Now Ra lambda is equal to R infinity. So we have defined R infinity like that right before. So now calculate this expression II at x equal to L, right? Then what do we get if you just plug in x equal to L? You get V cos h L minus V naught, because this part becomes 1. So Ra lambda becomes R infinity. So you will have now this whole thing, which is the axial current at the far end, is equal to VL VL by RL. That is the loading current, right? So because you have, so this is RL, this is VL. So the actual current is nothing but VL by RL. So if you plug this in and also use this and move things around a little bit, you can solve for VL, and you will get this. VL is equal to V naught RL by R infinity sin HL plus RL cos HL. So here we pretty much have all known quantities, except we still have this problem. V naught is something that we assume. We still have not expressed V naught in terms of all the other known quantities. As what is known is injected current, I naught, and R infinity and RL and L, right? So V naught is an assumed quantity. We need to find out what it is. So if you plug this VL into this expression, right, it's again a bit of a problem to simplify it. If you plug it in here, you will get something like this. So because the expression we have here on equation 15 is in terms of VL and V naught, it looks like this. So let's start with that and plug in this VL expression here. Then we have V naught sin h L minus x plus, so VL is this huge expression, V naught by R infinity by RL, etc., times sin h x by sin h L. So in the numerator, move this expression out and merge this with the denominator. Then you have this expression in the numerator. V naught comes out, right? R infinity by RL times sin HL plus cos HL. This whole expression times sin HL minus x plus sin HX. So if you expand this numerator term again a little bit, and then you will get this, and you also use this rule on the right side. So cos HL times, this is a bit of a trick here, cos HL times sin HL minus x plus sin HX can be written as, first term is the same, second term I'm writing as sin h of capital L minus L minus x. Okay, so if you expand this part, right? Then you can cancel out this part and this part. You get this. So you can add up the first two terms into one expression. Now plug this back in here. So this is what, if you plug this in, you get this. Now you can cancel out sin HL here. So you will get V naught times R infinity by RL times sin H of L minus X plus cos H of L minus X by R infinity by RL times sin H of L plus cos H of L. Okay, so finally we have this this expression, and now in this expression I want you to do a small homework. You can try this later. So what happens when L goes to infinity? Right? Just check if you'll get the voltage. So if L goes to infinity, it becomes a semi-infinite cable. Right? So you should get the solution for the semi-infinite cable. Just work it out as a small homework problem. Now we need to find out the input resistance. So that's something we've been doing for all cases. So here, how does it work? So input resistance is nothing but V naught by V naught by II, right, at x equal to 0. So how do you find this out? II is equal to minus 1 by Ra times dou V by dou x. Okay, so V is a VM is a big expression now. Differentiate that, right? It's not a big problem. So you have again Ra lambda, which is R infinity. So you plug that in, you have and right, you reduce the expressions a little bit, you get this. So R infinity, so Rin is equal to R infinity times R infinity gran HL plus RL by RL tan HL plus R infinity. So if you in this expression, if you take so how do you calculate the case of open and sealed and killed end and sealed end? Can somebody tell me? So you should get those two as special cases from this expression. Can somebody work it out? Oops. Hello. Yeah. So what is killed end and what is sealed end? Anybody awake out there? Okay, Guru Pramod. What is sealed and what's killed end?
Yes, sir.
What is a sealed end? What is a killed end? How do you express it in terms of this formula? So this formula is a general formula. Rn is equal to R infinity, all this stuff. This is
Yes, sir.
general formula for an arbitrary loading resistance. Right? I'm saying this is more general than the previous two. So you should be able to derive the previous two from this. How do you do that?
Okay, let me see.
Anybody has any comments?
So you set RL to 0 and infinity.
Yeah, very good. So can you solve this? RL equal to, so killed end is shit. So RL is equal to 0. Sealed and RL is equal to infinity. So if you plug it in, what do you get in this? So RL equal to 0 is straightforward. You just get straight away, right? Rn is equal to R infinity times, right, tan HL. For RL equal to infinity, you have to divide by RL numerator denominator and all that, and then you have so you got R infinity by tan HL, right? So is equal to R infinity time cottage. So the previous two cases come as special cases of this more general case. So similarly, you can even work out the expression for the voltage distribution. Okay, so like that we were able to so derive some results for steady state conditions. We have done it for totally 5 cases, right? Infinite cable, semi-infinite cable, then finite cable. In finite, we have again 3 cases: RL equal to 0, RL equal to infinity, RL equal to RL, arbitrary. Okay, so now what do we do with these results? Because ultimately, what we need to do is we need to be able to do is, if I have a dendritic cable, dendritic tree with complex arbors and all that, and I should be able to find out. I'm assuming a simple case where I inject current into the mouth of the cable, mouth of the dendritic tree. I need to find out what is the voltage everywhere. Or even more general case is if I inject some current into at any point in this tree, I should find out how the voltage changes all over the tree. This is the most general problem. So thing is, if you want to solve the most general case, then you need to be able to solve the variation of voltage in with time. Whereas what we have done until now is just steady state conditions, right? If I inject constant currents, and if I wait until the entire voltage distribution goes to steady state, then what is the distribution like? Right. So we have really ignored the entire temporal variation, which is a more interesting problem. Right, because we are interested in signal propagation in the dendritic, not just what happens in steady state conditions. Because bend is never in steady state; only a dead bend is in steady state. So, but then since we go by the mathematical convenience, we start off with steady state conditions. But even the steady state, all that we have been able to do is start with something so right unrealistic like infinite cable, and go up to the point of a finite cable with arbitrary resistance. But this is itself is not really useful. Let us so our next target is to extend this theory to be able to solve the steady state conditions for an arbitrary dendritic tree. Even that is not very useful, but that's all that we can do right now with whatever experience we have gained so far. So therefore, let us now look at the case of branch cables, but again under steady state conditions. So this is also under steady state condition. So we'll come to temporal solutions later. So branch cable in a dendritic tree looks like this, right? You can approximate a dendritic tree like this in terms of a whole bunch of small uniform cables, homogeneous cables. So each cable you assume is a cylinder, where the properties are homogeneous along the length of the cable. And so divide the whole cable in whole dendritic tree into lots of small cylinders like that, and express it as a network of such cylinders. So now can you solve this system and find out the steady state voltage distribution? So let us take the smallest possible system like this, but we can easily generalize it to more general tree structures. I'll only solve it for this case, but you can easily extend this to more general cases. So let us say I have a dendritic tree in which there is a main cable denoted by 0, right, and there are 2 branch cables denoted by 1 and 2. And the properties of so each of them has its own R infinity values. I call this R infinity 1. This is R infinity 2, and this has R infinity 0. Similarly, they all have their own electrotonic lengths. So this is L0, this has L1, and this has L2. So now I inject some current into the main cable, into the mouth of the main cable. Call it I0. Now I need to find out the voltage distribution over the entire system. So let us start with the computation of input resistances. Right, let us calculate all the input resistances, right, and then we'll calculate the voltage distribution. Let's see. We'll see in a moment why it is necessary. So let us take these two branches first, and the input. So these are sealed ends because we assume that the dendritic tree ends here. So that says we're taking a small dendritic tree. Since it ends here, this is a sealed end. Therefore, the voltage, the Rn for this is given by R infinity 1 times cot h, right? So cot h of L1 for the first one, cot h of L2 for the second one. So you have R in 1 and R in 2, which are the input resistance of these two cables. So therefore, now you can express the system like this. You have the main cable, the zeroth cable, which has two loading resistances in parallel, R in 1 and R in 2. So since they are in parallel, I can apply the parallel formula and find out one loading resistance. I'll call this RL0 because it's the loading resistance of the zeroth cable. So therefore, once you know that the loading resistance of this one is RL0, we apply and now we can find out the input resistance of this whole thing, right? R in 0. We apply the previous formula, what we just derived, and since the loading resistance RL0, you get this. So you get your answer in terms of R infinity 0, which is in R infinity of the zeroth cable, and L0, which is the electrotonic length of the zeroth cable. So you have this expression. So now what we have, the question is, I inject a current I0 or I inch, sometimes I inch is used, then find out the voltage distribution over the entire system. So if my input resistance I know now, R in 0, if my input current is I inch, then V0 at the mouth of the entire tree is nothing but R in 0 times I inch. So I have V0 like that. So given V0 and given RL, I know how to calculate the voltage distribution for an arbitrary finite cable. Right? We have just derived that formula. So you get that result using equation 20, right? So then once you have that, so now you know the voltage distribution along the main cable. So let's say it's something like that. Right, so now what we do is we need to find out what is the voltage at the far end of this main cable so that we can calculate the voltage distributions for the branch cables. Right, so this is the expression. So Vx is given by this whole expression. Now, how do you find the voltage at this point? So at this point, the voltage is, you plug in x equal to L, actually x equal to L0 in the expression, in this expression, you get the voltage at the far end of the main cable. Right, so that will be, we'll call this point V12. I'll call this voltage V12 because that's the junction point for the branches 1 and 2. So this you calculate at L, actually it is L0, right? So you get V0 by this whole thing. So whatever it is, you get the value for V12. Now, given V12, how do you find the steady state voltages of cables branches 1 and 2? So since these are sealed and they have sealed and boundary conditions, the voltage distribution for this kind of a cable is given by the input voltage. In this case, it is V12 times cos h L minus x by cos h L. That's a general formula. So for cable 1, it is V12 times cos h L1 minus x by cos h L1. So that is the first expression. Whereas for cable 2, it is V12 times cos h L2 minus x by cos h L2. So you get this. So, right, so like that you can get V12 and so we'll call this expression V1 of x, right, and this expression V2 of x. You get everything. So like that you can calculate the steady state. So you can do the same thing over and over again and solve arbitrary trees. It's just recurrent, it's just repetitive. So basically, the summary of it is to start. So if you have a big tree like this, let's say you have something like this. Start with the far end from the terminals, right? Find out the Rn for this guy and this guy. Apply parallel formula. You can have multiple branches. It doesn't have to be always. It doesn't have to be a binary tree, or it can be arbitrary tree, right? Take start from the terminals. Uh, Find Rn for all of them, and they're all sealed ends. So Rn formula we know. So they're all in parallel. So apply parallel formula. You get the loading resistance of this cable, right? So then you find out the input resistance of this cable with the arbitrary loading. This cable with arbitrary loading. Then these two come in parallel. So apply parallel formula. Find out the loading resistance of the main cable. Right, so you can easily see that this can be done recursively to find out the input resistance of an arbitrary sized tree. So once you get Rn for the entire tree, so this is Rn for the entire tree, right? You apply I inject or I naught, and you get V naught. And once you have V naught here, you know the RL here. So apply the voltage formula for the main cable with arbitrary loading. Then you get the voltage for the main cable. Calculate the voltage at the far end of the cable by plugging in the value x equal to L naught in that expression. So you get the voltage here. Right, once you have the voltage here, then again it's the same pattern applied right to the next part, right? Because at any point, if I cut this tree, you'll get another tree, the smaller tree. So the same pattern is repeated. So like that, you can find the voltage distribution of the entire cable, but this is not going to solve our ultimate problem. Within our ultimate problem, I should be able to inject current anywhere, and also find out the voltage variation through time. Okay, so we'll get there slowly, but with the current steady state analysis, this is all that we can do. Okay, so I'll skip this Raoult's condition stuff. So what we'll do now is I'll introduce the steady state solution problem, and then we can actually look at the solution in the next class. So, sorry, there's time dependent solution problem. We can actually look at solution next class. So this was our complete cable equation, right? What we derived, I think, a couple of weeks ago. So where you have lambda square, dou square Vm by dou x square, and now you see that again the variables are small x and small t. So this is on the left side, and you have tau times dou Vm by dou t plus Vm minus I inch Rm. So this is the full cable equation. So now let us make a substitution in this, and we'll see that you get slightly simplified expression. So we have seen that the lambda is a space constant and tau is a time constant, right? So therefore you can rescale both space and time again, like what you have done in case of steady state conditions for x, right? You can rescale both space and time variables right now and get a slightly simplified expression. So how do you do that? So let us define a new function, new voltage function, Vm bar, which is a function of capital X and capital T, right? And I'll assume that it is in this new, just new variables, but the same quantity. So that is same as Vm at small x small t at the corresponding values. So what's the connection between Vm and so right? How do you get the new derivatives? So dou Vm by dou x is equal to dou Vm bar by dou capital X. So this is right by dou x by dou small x. So this is 1 by lambda, right? So you get this. So similarly, if you do dou Vm, sorry, dou square Vm bar by dou x square, you get 1 by lambda square times this. Okay, so this is the spatial derivative works out like this. If you look at time derivative again, so dou Vm bar by dou t is equal to dou Vm bar by dou capital T times dt by dt, d capital T by d small t. And this is equal to 1 by tau m. So you get this. So the derivatives are somewhat straightforward. But what is a bit tricky is how to deal with the I inch. Because I inch is a function of the original I inch is a function of small x and small t. How do you express it in terms of capital X and small capital T? So now we know that I inch is a current density. That is current passing per second per unit length, right, of the cable. So right, it's a density both in space and time. Now, how do you convert this into the new variables? Because both space and time variables are now rescaled by some factors. So let us define a quantity capital Q at xt, right? So if I have a cable like this, let's say this is the origin of the cable, and I define a quantity called capital Q at xt, which means the total charge that has passed through the cable. Okay, so from outside to inside, the external injected charge because of the external current. Total charge that passed through the cable in this stretch of the cable, this is x, right, and up to this time 0 to t. Okay, so let us call that quantity. Now that quantity is the same. So instead of small x and small t, if I use new variables capital X and small capital T, right, the corresponding capital X and capital T values, then the charge that has flown into the cable is still the same. So I'll call this new charge, which is in terms of capital X and capital T. I'll call this Q bar. So Q bar is equal to Q, right? If you work out, you apply the corresponding values of, right? That is capital X is equal to small x by lambda, etc., etc. So we know that I inch, since I inch is a current density in terms of both space and time, and in terms of both x and t, it is given as dou square q by dou x dou t, right? Because current density. So if you apply this, then you can, in a very straightforward fashion, you get so dou square q bar capital X capital T by dou x dou t, dou capital X dou capital T, right? And this second derivative, right, is you just get a factor of 1 by lambda tau m. Okay, so you get this. So with this, you plug it into the. So this is worked out in this paper by Tuckwell from 1988. So you plug it into this formula again, right? You get this new factors. So this, so the Vm is right now that special derivatives are in terms of capital X. So lambda square is 1, and this must be capital T. Tau is gone. So plus Vm minus I inch xt by lambda Cm. Because I have this new factor lambda tau m, right? So once you have in this reduced expression, reduced equation, the solution. So let us apply this for infinite cable, right? The boundary condition is Vx equal to 0. So at so no matter how much current you pass and where and all, assuming all your currents are finite, right? At infinity, the voltage is 0 on both sides, and now I'm injecting, like just like in case of the infinite cable under steady state conditions. Here also I'm injecting delta current, right, which is an infinitely brief pulse, which is given by I naught into delta t and delta x. Sorry, yeah, it's not even, in case of steady state we used ut, which is step current. Here I'm using delta current both in space and time. That is, I just squirt a little bit of charge into the cable very briefly, very quickly, at time t equal to 0 and space x equal to 0. Then how does the voltage vary? So the answer to that, I'm giving without proof, right now is this. V of capital X capital T is equal to I naught Rm by 2 lambda times root of pi capital T. T is a time variable times e power minus x square by 40 times e power minus t. Okay, so how does this expression look like? What does it look like? It looks something like this. So at some finite t, right, it will look something like this. So this is a Gaussian in space times another e power minus t. So at some, okay, so let me just state that this equation, you get a similar expression if you solve the diffusion equation. So this equation, right, is very similar to the diffusion equation where you have some dou square c by dou x square is equal to some d times dou c by dou t. Okay, this is a diffusion equation. The solution to this will be of this form, just the Gaussian part without this extra e power minus theta. Okay, so it will be a Gaussian which is spreading with time. That's the solution of diffusion equation. But the cable equation has an additional term Vm, so therefore we have an additional term here which is e power minus t. So let us stop here. We already covered a lot of stuff in this class. So tomorrow we will analyze this expression and try to see some meaning in it, and we'll also see how this voltage varies with time and space. Let's try to get an understanding of this expression, see how it varies with time and space. So any questions? The thing is, once you solve for the solution for the delta current, right, the impulse current, impulse both in space and time, then the more general current, which is given everywhere in the cable and for all time, right? So more general current, that can be calculated simply by convolving this impulse response, what's called impulse response in electrical engineering, right? So V delta, if I give input as impulse, is the impulse response of the cable to the impulse current. That you convolve with the general current, and you get the general solution of the voltage. Okay, so anyway, let us spend some more time on this and try to understand the nature of the solution. So let us stop for now. Any questions? So because it's a PPT and I don't have to work out all the math, it goes a bit fast. And normally on the board, when you work out all this, it takes a lot of time. So I don't want to go too fast and confuse you. All right, please let me know if you have any questions. Okay, so I'm doing all this biophysical stuff because this is a big part of computational neuroscience. Although my lab doesn't do much of this kind of modeling, it is a big part. Tomorrow, if you go to some lab, if you want to do computational neuroscience, it's very likely that that lab will be doing something like this. All right, these are the elements. So I thought it might be useful. Okay, so